ブルーキャットの方を見れば、こう書いてありますね。2022年3月4日、9時から開始っていうことなんですけれども、追いかけ再生とかができると思うので、そろそろ始めたいと思います。それで今日は第2章のパート2の、286ページからです。で、本はここに書いてあるような、ここに Amazon がありますけど、このサスキンドという人が書いたクォンタムメカニクスの第9章です。それで、ちょっと音がめなしにしてもらいたいんですけど、テキストはここにあります。ここからダウンロードできます。で、ダウンロードして、それで、290何ページだっけ。ちょっと待ってください。ここに書いてますよ。これ、モーターがうるさいな。286ページ。286ページなので、あれないだ。286ページ。どこだ。3、4、5、6ね。ベロシティ&モメンタムっていうところからやります。ここからやります。さて、リツイートしてもらった。で、これで YouTube をこう見れば、自分が映ってるかなっていうことがわかると思うんだけど、16ページ。出てますね。はい、出てます。ということなので、始めたいと思います。9.4 章のベロシティ&モメンタムです。 So far, I haven't explained the connection between the operator P ちょっと待って。その前にこのツイッターの方行っていただいて、ハッシュタグSusskindQM です。これね、ハッシュタグSusskindQM。これをクリックしてもらえれば、次回の予定を入れる、あれ出てこないな。あれサスキンド付け忘れたかな。これか。これですね。次回の予定が入れられるようになってます。それで、早速入れていただいた方がいるので、次回は、明日の9時ということでやりたいと思います。で、どうなってんだこれ。入れられるのは、明日のサタデーの3月5日サタデーの、予定を1時間刻みに入れられていて、今のところ9時と。この YouTube ライブが終わる頃にも、これ変わってなければ、3月5日の、9時ということで確定したいと思います。はい。Velocity and momentum. So far, I haven't explained the connection between the operator P and the classical notion of momentum, namely mass times velocity, or V equals P over M. So, この運動量 P っていうのは実は、必ずしも MV であるとは言っていたかった。これまでで。ここに来るまでに、このモメンタム P っていうのは MV のことであるよということは言ってませんでしたよと。つまり V というのは P 割る M であるとはまだ言っていませんよと。そういうことを言っています。What do we mean by the velocity of a quantum mechanical particle? さあ、それではじゃあこの速度、P 割る M で定義される速度、P 割る M で定義されているのかどうかちょっとわかんないですけど、velocity、量子力学的な粒子の速度ということで何を意味するでしょう。 The simplest answer is that we mean the time derivative of the average position psi x psi。 これはつまり期待値ってことね。その粒子の位置の期待値 1x の期待値ということです。で、この粒子の、位置の期待値が、時間とともにどうなる、時間っていうか、それの時間変化がどうなるかと。だから、時間微分するとどうなるかっていうことで、速度を定義しようと。Or more concretely, in terms of wave function, we can write v equal ddt integral psi star x psi dx. So this part, この部分が、psi x psi ということです。で、この位置の期待値を、時間微分することで速度を決めると。Why does psi x psi vary with time? Because psi depends on time, and in fact we know just how. これから説明があるかな。psi が時間に依存する、負債が時間に依存するよっていうことはこれから説明するのかな。The time dependence of psi is governed by the time-dependent Schrödinger equation, we could use that fact to work out how psi xi varies with time. I've done it this way by brute force, and it takes several pages. どういうことなのね。Fortunately, the abstract methods you learned in earlier lectures make it easier. In fact, we could use that fact to work out. Anyway, これはちょっとよくわかんない。Let's skip this sentence. Strange sentence. Fortunately, the abstract method you learned in earlier lectures make it easier. 何でしょう Abstract method. これはだから多分 X これはこういうことじゃなかったっけ。なんかこういうことだと IH バーブルと1からなんかこういうことだと思うね。Abstract you learned in earlier lecture make it easier. In fact, we have already done most of the work in lecture 4. In fact がいっぱいあるような気がするんだけど。In fact, before we proceed, I recommend that you review lecture 4, especially section 4.9, from the beginning to the appearance of equation 4.17 to restate equation 4.17. どうしようかね。いるかな。いるかな。先に進もうかな、これは。So, as I said, this is the thing. I think mine was wrong, probably. Maybe okay. I think mine was wrong in a sense. This one, this has to be this, and this has to be expectation value. Then let's see. This has to be time derivative of expectation value. Time derivative of expectation value of x is this one, I over h bar multiplied by commutator xh. You have to remember you put h in the second position. Okay. So this is called Heisenberg equation of motion. Heisenberg equation motion. I don't think we should review chapter 4. We just have to accept this fact. We accept this as a equation formula, some proved formula. We accept. Okay, so this goes like this. This can be, oops, it's different. Sorry, I think I was wrong. In this case, I need minus sign here. This has to be minus I. Yeah. Okay, so I follow the other way. I follow the other way around. I'm sorry. So let's follow the textbook. We have to put H first. Sorry, H, not the second place. First place we put H, then X, and factor is I over H bar. I over H bar, then put H and X. So you can just see, you replace ddt by this one. This second position is X. Yeah? Maybe this is okay, anyway. I shouldn't say too much. Okay, so this is the Heisenberg equation of motion. You have some physical observable, and you consider the time derivative of that expectation value, and right hand side is you have H. This is just replacement of ddt. Instead of ddt you put H, and also a factor I over H bar. Then you put comma physical observable. In words, the time derivative of the expectation value of any observable L is given by I over H bar times the expectation value of the commutator of the Hamiltonian with L. Applying this principle to the velocity v, we find that v, why this is true? V is I divided by 2mh bar p square comma x. Why is it true? Do we have Hamiltonian? Do we have Hamiltonian already? Where is our Hamiltonian? Where is our Hamiltonian? Very strange. Do we have our Hamiltonian? This is our Hamiltonian. Okay, so this is our Hamiltonian. Okay, so we put this Hamiltonian to here. See, we put here x, so here x, and for h we put p square over 2m. Yeah, so we put 2m outside, so you obtain this one. We obtain this one. Now, all we have to do is compute the commutator of p square. Commutator of p square and x. A couple of simple steps shows that p square x equal, you can just check. This is like p. So this was IH bar, right? Was it IH bar? This relation can be confirmed by expanding each commutator and spotting some obvious cancellations. Okay, anyway, so this one is like px minus xp, and this is px minus xp p. Yeah, so we have pxp yeah, I think we can cancel this pxp and pxp. So that what is left over is p square x minus x p square. So that's this one. So you can confirm this way. This relation can be confirmed by expanding each commutator and spotting some obvious cancellations. Prove equation 9.10 by expanding each side and comparing the result. Yeah, I think that's just what I did. P square x minus xp square. That's the left hand side. On right hand side we found p square x and xp square. The last step uses the standard commutation relation. So this is important result. Okay, what you should do is like you can this is something you have to remember. P equal h bar over I ddx. This is the P. Then you put this one. So you consider I h bar d dx and x psi x. This is something you have to consider. Then you will see this part will be just like IH bar minus IH bar. Okay, so that's why you have this commutation relation. Okay, what you shouldn't forget is this one. You have to consider this one, including this function. You have to consider commutator, including this additional arbitrary function psi. Then you can take derivative. You just expand the commutator like AB. This is a commutator. This will be expanded like AB minus BA. But commutator, you always have to have some function afterward. Okay, so then you will see this relation. I think we have done this before. Substituting this into equation 910 and plugging that result into equation 9.9, we find that. Okay, so this is like I. This is minus IH bar. This is also minus IH bar. So what we have is minus 2 IH bar for this commutator. Minus 2 IH bar P. Yeah. So this is like this. This is more like 2 MH bar I minus 2 IH bar P. Okay, so then we cancel 2 I minus I H bar. So what we do, what we have is P expectation value divided by M. Yeah, so we have this one. V equal expectation value of P divided by M. Or perhaps more familiarly, P expectation value equal MV. We have proved exactly what we set out to prove. We have proved exactly what we set out to prove. The momentum is equal to the mass times the velocity, or more exactly, the average momentum equals the mass times the velocity. To get a better idea of what this means, let's suppose the wave function has the form of a packet or fairly narrow lamp. The expectation value of x will be approximately at the center of the lamp. Lamp は塊。これ塊。What equation 9.11 tells us is that the center of the wave packet travels according to the classical rule P equal mv. 9.5 Quantization. Before moving on to the subject of forces in quantum mechanics, I want to pause forces in quantum. I want to pause and discuss what we have done. We have started with a well-known and well-trusted classical system, the free particle, and quantized it. We can codify this procedure as follows. Codify. What is codify? Codify. コーディファイ成分化する体系化する成分 By the way, I can check my see where is it my YouTube. Where is my YouTube? So strange. Here this is okay. It's a new one first. So here, right? Is there a comment? Save. By the way, I can check my. I can see the comment from time to time. So please type in your comment so that I can check. See here, right? If I don't echo my voice, it's okay. Then I can check comment. So I try to check comment from time to time. So if you have questions, please don't hesitate to type in. Or you can ask me by Twitter or this field in BlueCat. You have this comment field. Also in Compass, you have field to type in comment. You can also ask me by Twitter. So by any method, you can ask me any question. And quantization. Before moving on to the subject of forces in quantum mechanics, I want to pause and discuss what we have done. Okay, that's good. I want to pause and discuss what we have done. We started with a well-known and well-trusted classical system, the free particle, and quantized it. we can codify this procedure as follows. Number 1, let's start with a classical system. This means a set of coordinates x and momenta p. In our example, there was only one coordinate and one momentum, but the procedure is easy to generalize. I don't know. I don't know. Okay. Procedure is easy to generalize for higher dimension system. But I don't think we should generalize it. We can just work on one coordinate, one momentum. The coordinates and momenta comes in pairs, xi and pi. Okay, so this is already generalized. If we have three components, three coordinates, x1, x2, x3, then there are also three momenta, p1, p2, p3, or x, y, z, px, py, pz. Okay, the classical system also has a Hamiltonian, which is a function of the x's and p's. Okay. Replace the classical phase space. What is a phase? Okay, classical phase space. This is like this. X, Y, Z, Px, Py, Pz. 6-dimensional space. This is like, I would say, one particle phase space. One particle phase space is the 6-dimensional space which has an axis x, y, z, px, py, pz. You have 6 axes. So this is a 6-dimensional space. And one point in this 6-dimensional space is the state of this one particle. And this is a phase space, in classical mechanics. So replace the classical phase space with a linear vector space. That's hard. So we replace. This is classical. This one particle in phase space. This is one particle phase space is a 6-dimensional space. This is the classical mechanics. So we replace this phase space to a linear vector space. What is linear vector space? In the position representation, the space of states is represented by a wave function psi x that depends on the coordinates in general of them, all of them. What's all of them? Space of states represented by a wave function that depends on coordinates. All of them. I don't understand this. Maybe this one. This is this. depends on all of the coordinates. So this x is actually x, y, z. If you have two particles, this coordinates is x1, y1, z1, x2, y2, z2. This is two particles. If you have three particles, you have x1, y1, z1, x2, y2, z2, x3, y3, z3. 9 coordinates. So this wave function psi depends on all of the coordinates. If you have three particles, you have 9 coordinates. If you have one particle, you have 3 coordinates, all of them. Okay. And number 3, let's please replace the x's and p's. X and p's with operators xi and pi. Each xi acts on the wave function to multiply it by xi. Each pi acts according to the rule. So this one, I remember this way. H power over I. So this one is equal to IH. This is easier to remember. I downstairs, H bar upstairs. So you just put H bar I, del del x. This is px. This is p. You just remember this. If you want to put subscript I, you can just put I. Okay. When these replacements are made, the Hamiltonian becomes an operator that can be used in either the time-dependent or time-independent Schrödinger equation. The time-dependent equation tells us how the wave function changes with time. The time-independent form allows us to find the eigenvectors and eigenvalues of the Hamiltonian. So this is also important. Time-dependent equation tells us how the wave function changes with time. Then time-independent form allows us to find the eigenvectors and eigenvalues of the Hamiltonian. So there's a different roles for time-independent Schrödinger equation and time-dependent Schrödinger equation. Okay, these two Schrödinger equations have different roles. This procedure of quantization is the means by which the classical equation of a system converted to quantum equations. It has been used over and over in fields ranging from the motion of particles to quantum electrodynamics. There have been attempts to quantize Einstein's theory of gravity, but it was not so successful. As we saw in our simple case, the procedure guarantees that the motion of expectation values is closely related to classical motion. As we saw in one simple case, This procedure guarantees that the motion of expectation values in quantum mechanics is closely related to classical motion. All of this raises a chicken and egg question. Which comes first, classical theory or quantum theory? Should the logical starting point of physics be classical or quantum mechanical? I think the answer is obvious. Quantum mechanics is the real description of nature. Classical mechanics, while beautiful and elegant, is nevertheless an approximation. 近似。古典力学は量子力学の近似でしかありません。Roughly speaking, it holds true when wave functions maintain their shape as packets. Roughly speaking, it holds true. It holds true when wave functions maintain their shape as packets. Sometimes we are lucky and the quantum theory of a system can be guessed, and that's all it is. A guess. By starting with a familiar classical system and quantizing it. Sometimes this works. The quantum motion of electrons, deduced from the classical mechanics of particles, is a case in point. Quantum electrodynamics, deduced from Maxwell's equation, is another. But sometimes there is no classical theory to use as a starting point. The spin of particle has no real classical counterpart, and the quantization of general relativity has largely failed. できてないってこと。一般相対性理論の、量子化はできてませんっていうことですね。Quantum theory is probably much more fundamental than classical theory, which generally should be understood as approximation. Quantum theory is probably much more fundamental than classical. Classical theory generally should be understood as an approximation. Okay. That being said, I will now continue to quantize the motion of particles, but this time incorporating the effect of forces. ちょっと待ってください。ちょっと休憩っていうか、ちょっと待ってね。この辺、よかったら、もうちょっとちっちゃくしようか。どこだ？これぐらいちっちゃくしても読めるかな。この辺にしとくか。ちょっとこの辺読んどいてください。はい、すいません。時間はまだいいかな。forces。次のセクション。9.6 のセクション forces。The world would be a dull place if all particles were free. Forces are what make particles do interesting things, such as assembling themselves into atoms, molecules, chocolate bars, and black holes. The force on any given particle is the sum total of the forces exerted on it by all the other particles in the universe. In practice, we usually assume that we know what all the other particles are doing and replace their effect by a potential energy function for the particle that we are studying. This much is true in both classical and quantum mechanics. The potential energy function is denoted by Vx. In classical mechanics, it's related to the force on a particle by the equation. In classical mechanics, it's related to the force on a particle by the equation. Okay, this is called potential energy theorem. This is potential energy theorem. So what is the force? This is a force. Force is a derivative of potential with minus sign. You have one minus sign. This is you can say this is a definition of potential energy. If the motion is one-dimensional, the partial derivative can be replaced by an ordinary derivative, but I will leave it as it is. If we then combine this equation with Newton's second law, F equal ma, we get m d square x dtx, this is the force, equal minus del v del x, partial v partial x. In quantum mechanics, we proceed differently. We write up Hamiltonian and solve the Schrödinger equation. Incorporating the potential energy into this program is straightforward. The potential energy Vx becomes an operator V that gets added to the Hamiltonian. What kind of operator is V? What kind of operator is V? The answer is easiest to express if we think in the language of wave function rather than in terms of abstract Brown's cats. Easiest to express if we think in the language of wave function rather than in terms of abstract Brown's and cats. When the operator V acts on any wave function psi x, it multiplies the wave function by the function Vx. So operator V acting on the state psi can be understood as Vx multiplied to psi x. Just as in classical mechanics, once forces are included, the momentum of a particle is not conserved. In fact, Newton's law of motion can be stated in the form dp dt equal F. I think you understand. This is because P is mv. Yeah, and v is dx dt. So dp dt, this is m times d second derivative x dt second. That's why you can write Newton's equation of motion in this way. Or then you can use a potential energy theorem. And F is this. So the rule of quantization requires this is a classical case, classical Newton's equation. And here we switch. The rule of quantization requires us to add V to the Hamiltonian in quantum mechanics. The above red line is classical mechanics, and below the red line is quantum mechanics. So Vx in quantum mechanics, we have to add Vx to Hamiltonian and modify the Schrödinger equation in the obvious way. So original Schrödinger equation look like this. IH for partial psi, partial t equal H. This way. Yeah, then you plug in, you put this H to this H. Then you obtain this one first. Yeah? The second one is this. You have H psi equal E psi. This is time independent. Independent Schrödinger equation is second one. The first one is time dependent. Time dependent Schrödinger equation is the first line. What effect does this have? So putting a V, what is the effect of putting V? The additional term certainly affects the way psi changes with time. That of course must be so if the average position of a wave packet is to follow a classical trajectory. That of course must be so if the average position of a wave packet is to follow a classical trajectory. What is it? Footnote 4. I don't see a footnote number 4. Okay. Add V to the Hamiltonian. Technically, this is true for free particles as well. However, in the case of free particle, we set Vx equal to 0. Okay, anyway. To check our reasoning, let's see if it does. First of all, does equation 911 still hold? What is 911? Equation 911 still hold. What is 911? I don't know. There's no 911. Strange. Okay. P, expectation P is PV. 911 still hold. It should. Because the connection between momentum and velocity is unaffected by the presence of forces. This is from classical mechanics. This guessing is from classical mechanics because the momentum and velocity is unaffected in the presence of forces in classical mechanics. So that's as far as in the world classical mechanics is believed to hold, the same principle should hold in quantum mechanics as well. So that's why, because in classical mechanics, momentum, the connection between momentum and velocity is unaffected by presence of force. The same result should hold in classical quantum mechanics. That's what he is saying. Because a new term has been added to H, there will be a new term in the commutator of X and H. Yeah, potentially, that could modify the expression for velocity in equation 9.9. But it's easy to see that this doesn't happen. The new term involves the commutator of x with v, but multiplying by x and multiplying a function x are operations that commute. In other words, I think this is a little bit complicated, so I will try to work out myself. Okay, so today we went up to 293, so I will change this. 293. あれ 293. Then this is part 3. Then this will be the 7th. Okay, so then let me see. Let me decide the time for the next day. Next session. Let me see. I will change. I will decide the next session. Oh, this is strange. So this is, see, there is nobody. Okay, one more people voted this one. So I decide March 5th. Is it okay? ちょっと待ってね。これどうやるんだ。編集。I will do March 5th. 9 o'clock. Okay, March